In this presentation, we will try to understand what is big O notation and how it is helping us in finding the growth rate of the function. So let's get started. Big O notation is used to measure the performance of any algorithm by providing the order of growth of the function. It gives us the order of growth of the function. That is what big O notation is all about. This notation is helping us in providing the order of growth of the function, how a particular function grows. It gives the upper bound on a function by which we can make sure that the function will never grow faster than this upper bound. So it gives us the least upper bound on a function so that we can ensure that the function will never grow faster than this least upper bound. We want the approximate runtime of the operations performed on data structures. We are not interested in the exact running time. From the previous discussions, it is clear that we are not interested in exact running time. We are interested in approximate runtimes. Big O notation will help us achieving the same. It gives us the approximate runtime. Obviously, it gives us the order of growth of the function, the least upper bound on a function, so that we can ensure that the function will never grow faster than the upper bound specified. Let's see the formal definition. If fn and gn are the two functions, then fn is equals to big O of g of n. If there exist constants c and n naught such that fn is less than or equal to c dot gn for all n greater than or equal to n naught. It says that we have two functions fn and gn. We are basically comparing these two functions. We can say that fn is equals to big O of g of n if and only if there exist constants c and n naught. We must have these two constants such that fn will become less than or equal to c dot gn, okay, for all n greater than or equal to n naught. So these are the two constants c and n naught. C must be multiplied by gn so that fn will become less than or equal to c dot gn. And this must be satisfied for all n greater than or equal to n naught. These two constants we have to find out. This simply means that fn does not grow faster than gn. Fn equals to big O of gn simply says that fn does not grow faster than gn because we are providing the upper bound on f of n, right? So it will never grow faster than gn. That's what this concept says. So we are basically providing the growth rate of the function, which eventually gives the worst case time complexity. Isn't that so? Because this is the upper bound on this function, which simply says that this function will never grow faster than this. And it means that we are actually calculating the worst case time complexity, how worst a particular algorithm can perform. Now let's see one example. Let's say fn is equals to n and gn is equals to 2n. We need to compare these two functions, let's say. We need to find is fn is equals to big O of gn or not. For this purpose, according to the definition, we have to write something like this. Fn is less than or equal to c dot gn. We need to find some c value here. Let's first replace fn by n and gn by 2n. This gives n less than or equal to c dot 2n, right? We already know that n is less than 2n. If we take c equals to 1 and n not equal to 1, this will definitely satisfy. So after replacing c by 1, this becomes n less than or equal to 2n, which is true. We can take any n value starting from 1, it will always satisfy. If we take n value equal to 1, then 1 is definitely less than 2. So for n not equal to 1, this will satisfy. So we have some constant c and some constant n naught for which n is less than or equal to 2n. So fn is equals to big O of 2n. Or in other words, we can say that fn function will grow linearly. We can replace this gn by 2n easily. Also, we can eliminate this constant term in front of this n because it doesn't matter if we eliminate it. Fn will grow linearly. And that is what is written over here. Obviously, it will grow linearly, right? Now let's see another example. Here fn is equals to 4n plus 3 and gn is equals to n. We need to find is fn is equals to big O of gn. For this purpose, again according to the formal definition, we have to put something like this, that is fn is less than or equal to c dot gn. We can clearly see that 4n plus 3 is not less than or equal to n, but we need to find are they asymptotically equal. Let's replace fn by 4n plus 3 and gn by n here. After this we get 4n plus 3 less than or equal to c dot n. We need to find some constant value c such that 4n plus 3 will become less than or equal to n. Let's take c equals to 5. Obviously we need to choose higher value, right? Here it is 4n. Let's take c value equals to 5 such that it becomes 5n. Then the inequality will be 4n plus 3 less than or equal to 5n. Now we need to find the constant n naught such that this will satisfy for all n greater than or equal to n naught. This means we need to solve this inequality. Let's solve this. 3 will be less than or equal to 5n minus 4n. This gives n greater than or equal to 3. So this inequality satisfies for all n greater than or equal to 3. Therefore, we can say fn is less than or equal to c dot gn for all n greater than or equal to 3, where c is equal to 5. Here you're choosing the constant c as 5 and n naught is equals to 3. Here this is the n naught value. For all n greater than or equal to 3, this will satisfy, which eventually means fn is equals to big O of n. We can replace this gn by n. Then this fn will be equal to big O of n, which means that the growth rate of this function is linear. It will not grow faster than n, which simply means that the growth rate of this function is linear. It is not the case that suddenly it will behave like a quadratic function. It always grows linearly. And we can clearly see from this function as well. This is 4n plus 3. These are constants, right? And this is the n term which is playing the important role. Fn equals to big O of n simply means that in worst case, Fn can grow linearly. Now let's analyze the growth rate visually. For this purpose, I have created this table for different n values and how Fn and Gn are changing with different n values. Let's plot this on a graph and this is what we get. This blue line, which is the light blue line, represents the Gn and this dark blue line represents Fn. This is linear growth. So the idea of big O notation is to give the upper bound on a particular function and eventually it leads to the worst case time complexity. Actually, big O notation is giving us this ensurety that this function will not suddenly behave like a quadratic function or a cubic function or will not grow exponentially in future. It just grow in a linear fashion. So the worst case could be a linear growth, not greater than that. This is the meaning of big O notation. And this is how we are using big O notation to find the time complexity or the worst case time complexity of any algorithm of our choice. Okay friends, this is it for now. Thank you for watching this presentation.